All right, everybody. Thank you so much for joining. I'm really excited to give you this presentation today, and it's brand new, so I really hope that you like it, and I think you're going to find a lot of value in it, especially for all the installers I see joining us. I'm sure you guys are going to like this one. This presentation is titled Safety and Standards. My name is Matthew Walker, and I am the trainer and tech support here at SimpliPhi Power. Just want to start with a bit of housekeeping. If I could ask everybody to just put their questions in the Q&A section at the top or bottom of your screen, that would be awesome. I will probably cover a lot of those questions during the presentation, but if I haven't, I'll definitely address your question live at the end of the presentation. There's no use in raising your hand unless there's been some crazy, audio catastrophe and you can't hear me, then just put your questions in the Q&A because I cannot unmute you. Awesome. So let's get started without further ado. Again, this is the safety and standards presentation, and I'm going to begin with a quick overview of our company here at SimpliPhi Power. So all of our energy storage solutions are safe, proven, and simple. When I say safe, I mean non-toxic, non-hazardous, cobalt-free chemistry. This means there's no risk of thermal runaway or fire propagation, and additionally allows us to prevent child labor in our supply chain. Our batteries are UL certified, 1642, 1973, and 9540 where applicable, and UNDOT certified, 3480 and 38.3. And if those mean nothing to you, don't worry. We're going to talk a little bit more about them later in this presentation. Our batteries are proven with over a decade of experience and growth. They've been tested by the U.S. Army and Marine Corps. And again, we have special permission from the FAA to airship globally. That relates back to that UNDOT certification. Our business model also demonstrates that profitability and social impact can coexist. If you follow us on social media, you'll probably see that we're constantly getting involved in humanitarian projects, disaster relief, stuff like that. And so that's a main reason why I love working here, is because, our bottom line is more than just dollars and cents. When I say simple solutions, I mean that our batteries integrate and optimize with any generation source on or off grid. This is going to allow you to store energy for critical backup power, maximize your resilience and energy security, and create savings on your utility bills. Here at SimpliPhi, we have a global footprint now spanning over 40 countries and having over 100 megawatt hours installed worldwide. The problem we are trying to solve, at least 3 of them, are escalating energy costs. This is happening in the US and nationwide. Failing infrastructure. And if you're in California, like me, you've seen that you have little control over when your power is on or off, with the increasing number of public safety power shutoffs. Additionally, decarbonization is becoming more and more important, and it's being implemented by more and more cities. So to jump into the main content for today, we're going to talk about safety. I'm going to start with chemistry. And so I'm going to compare and contrast different lithium ion batteries for starters. Off the bat, we use lithium iron phosphate. That is our chosen chemistry. And these are some other lithium chemistries on the market right now. Lithium iron phosphate is, we feel, the safest because there is no significant danger of thermal runaway or fire, no toxic elements. The battery is actually landfill safe, even though, we'd love to see it recycled. If that's not possible, however, it can be landfill. It does not involve abusive mining practices in the supply chain. All of the materials are available widely and abundantly. And there's no ventilation, cooling equipment, or thermal monitoring equipment required for our batteries, as opposed to many on the market now. Additionally, lithium iron phosphate is able to withstand higher temperatures than most other lithium chemistries. So again, we have chosen lithium iron phosphate as our chemistry, and for our form factor that we actually use to build the battery, kind of the building block is, well, first I want to discuss the three options are the pouch cell, prismatic cell, or cylindrical cell. Pouch cells you'll often see in laptops. These are nice and compact, but they are easy to puncture or tear, and they can even swell. A prismatic cell is a little bit bulkier, a little more costly, and a cylindrical cell, think about, a AA battery. This has the longest cycle life, and it's got built-in short circuit protection. It's ultimately what we've found to be the best, longest lasting, and best performing battery. So that is what we use, lithium iron phosphate and cylindrical form factor in all of our batteries. So jumping further into safety, I want to talk about thermal runaway as it relates to lithium batteries. And I know a lot of us are probably really intrigued about this, but don't know exactly what it means. So thermal runaway is when a battery or cell of a battery becomes hot enough to basically start a chemical reaction, and that is going to fuel itself from there. So once the temperature reaches a certain temperature, different for each battery, it will essentially sustain itself and even get hotter from there. So this can cause off-gassing, fire, or explosion in lithium batteries. And what is this caused by? This is generally caused by a cell failure due to lithium plating or contamination during manufacturing. So those two things would cause a micro short circuit within the cell. And a short circuit, of course, means high current and high heat. So that could start a thermal runaway reaction. Thermal runaway could also be caused by an external heat source, like an unrelated fire that was already in your house, or a internal short circuit. Let's say you literally punctured the batteries with a bullet or a knife, or overcharging. Really anything that's going to increase the temperature of the battery or cells high enough to begin that reaction that becomes self-sustaining. Now, this is not a common occurrence by any means, but when it does occur, we want to make sure you understand what's going to happen. So during thermal runaway, and only during thermal runaway, electrolyte will actually vaporize, creating a flammable gas. Excuse me. If that gas is contained within the battery cell, the gas will not ignite, and there's really no catastrophe. However, if the gas escapes the cell, it's not only toxic, but also highly flammable. Now, lithium iron phosphate is so safe for many reasons, but one of which is that it can reach a higher temperature than NMC batteries before thermal runaway begins. Lithium iron phosphate can reach, for example, a ballpark of 200 Celsius before that reaction begins to be self-sustaining, whereas NMC and many other cobalt-based chemistries, that reaction begins much sooner, around ballpark 170 degrees Celsius. Lithium iron phosphate also reaches a much lower maximum temperature than NMC and other cobalt-based chemistries during a thermal runaway event. So even in the worst case scenario, LFP will reach a maximum of 400 Celsius ballpark during a thermal runaway event if it were to occur, whereas NMC and other cobalt-based batteries will reach a ballpark 675 degrees Celsius. And finally, another thing I want to point out is that lithium iron phosphate will release less gas than other cobalt-based chemistries during thermal runaway. So I really wanted to visually demonstrate the magnitude of the difference here. The amount of heat generated during thermal runaway is on the y-axis of this graph here, whereas the temperature is actually on the x-axis here. So you can see NMC is right here. This is the heat release versus temperature, and lithium iron phosphate is this dark blue line down here. And so it looks as if lithium iron phosphate just doesn't experience any thermal runaway. However, if you actually need to zoom in 100x just to see lithium iron phosphate in comparison to the other batteries, the other chemistries. So I think, again, this is just a really crazy demonstration of the scale of the difference here. And again, I just want to take a second to pause and remind anybody who's joined us late, please go ahead and put any questions in the Q&A section, and I will either get to them during the presentation or at the end, I'll answer the questions live. Cool. So we saw on the last screen the graph of heat released versus temperature reached of different chemistries. So as you could see, NMC and many other lithium chemistries were releasing a lot more heat than lithium iron phosphate. So what do you do to prevent a catastrophe? Well, with other batteries that are not ours, you often need cooling systems, ventilation systems, and thermal monitoring safety systems. So these are not only an added cost, but a point of failure on the battery, and they drain the battery's capacity parasitically. So these photos are examples I've actually taken from somebody's DIY battery off of YouTube, which you can check out here. I do think it is actually a really cool battery, and I don't want to rag on the build at all. I just use this DIY battery because it's a bit hard to find the internal composition of a lot of batteries on the market, of course, due to IP concerns. So this is similar to what you would see, however, though, if you bought one from a company. You'd see thermistors monitoring the temperature. You'd see this coolant system, a pump which circulates some refrigerant, and you'd see several fans likely on the unit to ventilate and cool. Now, again, think about your radiator on your car and how much of a point of failure that is and what a pain it is when it fails. So if the cooling system failed here, you'd have more than a pain. You would have a catastrophe potentially. And again, this is another benefit because with our batteries, you do not need cooling systems, ventilation, or thermal monitoring. So we've talked a lot about comparing the safety of different lithium chemistries. I also want to touch on lead acid. How do we compare the thermal safety, I guess you could say, with lead acid versus lithium batteries? So first off, there is such a thing as thermal runaway in lead acid, but it's not an exothermic chemical reaction. It's not going to necessarily cause your batteries to combust. It is really just when a lead acid battery gets warm or hot, it will increase its internal resistance decreases. So if it's on a charger that is not regulated, the charger will see that decreased resistance and increase the current, thinking it needs more charge. The battery will accept more current and get even hotter and then accept more charge and so on. So the reaction continues until the electrolyte is burned off at around just a bit above boiling temperature, 125 Celsius. So you may be thinking 125 degrees Celsius, that's not going to start a fire. However, during this thermal runaway event with a lead acid, there is off-gassing of hydrogen sulfide, which is not only toxic, but very explosive. It's flammable. So again, we have heard of and seen explosions with lead acid batteries not properly ventilated. And this off-gassing occurs somewhat even during regular charging. Hydrogen is produced during standard charging of a lead acid battery, which is why you need ventilation, because if the hydrogen is not vented, it is explosive. So we've talked a lot about the use of the battery and safety concerns there. I want to actually just rewind and talk about the production of the battery and safety concerns in that aspect. So lithium mining, as most of you likely don't know, and I didn't even know up until recently, lithium mining is mostly environmentally benign. It does not involve workers digging a big hole and going down there with pickaxes or headlamps. It's simply pumping water through an underground mineral or salt bed and into a large pond. And the sun will evaporate the water in this large pond and leave behind all the minerals and salts, which are lithium salts that are used in the electrolyte of the battery. Now, I saw this YouTube video, which is where I got these photos, and I was just amazed because I think I expected something along the lines of a coal mine, and seeing such a beautiful scene, kind of looks like an artist's palette. I was just surprised that lithium mining is this benign and beautiful. So what about the other components, though, in our batteries? Lithium, iron, phosphate. Well, iron and phosphorus, or phosphate, whatever you want to call it, they're both abundant. They're all, widely available and abundant. And all of these components are non-toxic and do not involve child labor, unlike cobalt, which we're going to talk about cobalt a bit further here. Cobalt comes primarily from the Democratic Republic of Congo. Now, there are some highly mechanized plants, but there's also plenty of workers just digging with their hands and, their simple hand tools. And it's estimated that about a quarter of the cobalt in the Democratic Republic of Congo is actually coming from black markets with no regulation at all. No workers' rights, no environmental impact reports, none of that. However, even the regulated mining, this is still subject to serious corruption from political leaders. I found this video on YouTube, which you can watch as well. It's basically explaining and showing you the mining process. People are just going and grabbing chunks of lithium chunks of cobalt, and you can see that they're telling the worker to be careful and go slow because otherwise it could collapse on him. So really, it just seems a bit unadvanced for me. I would love to see a lot more regulations here and a bit more safety for the workers. And I'm just really happy that we are not supporting this type of supply chain. So let's talk about the safety and standards that actually certify and guarantee that your battery is safe. First off, I want to talk about the UN standards, the FAA Air Shipping. So why are these standards necessary? They're necessary because since 1991, there's been over 200 separate incidents involving the combustion of lithium batteries on airlines. And if you recall, there was that Samsung Galaxy Note 7. Excuse me, I actually was one of the unlucky ones who had this cell phone and was not allowed to board an airplane. Had to leave my phone behind. So we have received special permission from the FAA to airship our batteries globally, and this is because they've undergone extensive testing. UN 38.3 is a certification for the batteries that I'm going to detail a bit in the next slide. And UN 3480 is for the packaging that the batteries must be shipped in. So if you ever think you're going to transport your batteries somewhere, be sure to keep the original packaging that is sent with your batteries. So now let's talk about the 38.3. What tests do the batteries undergo? I want to preface this first, though, by saying that these tests are just testing the battery's ability to not cause or go into a failure during these tests. It's not testing the operation of the batteries, and these conditions I would not recommend you do at home, and they're not necessarily covered under our warranty. With that said, knowing that it's not a good idea to do these tests, I'll just explain what tests were conducted, because I think it's pretty cool. So the batteries first are stored at high altitude. Actually, it's just a simulated high altitude, which is a very low pressure, much lower than sea level. Then the batteries are cycled between 72 degrees Celsius on the high end and negative 40 degrees Celsius on the low end in rapid succession. Next, the batteries are submitted to a vibration test, which is 36 hours of intense vibration testing. And then finally, actually not finally, there's more tests, but the fourth test is 18 impacts, which simulate repeated drops or crashes of an airplane. And to pass all these above tests, there must be no leakage, venting, disassembly, rupture, or fire during or after the test. And the open circuit voltage is also checked, has to be within 90% of the voltage prior to the procedure. There's a few more tests. The external short circuit, so the battery is going to be heated to almost 60 degrees Celsius and then short circuited between the terminals. So the battery cannot exceed 170 degrees Celsius and it cannot catch fire in order to pass. With the overcharging test, the battery is going to be charged at twice its maximum current and 1.2 times the maximum charge voltage recommended. It must not catch fire to pass this test. Oh, and again, I've been citing a lot of my sources down below. This is all public documentation. You can go through in more detail these tests if you'd like. But I wanted to save you guys from falling asleep today, so I just gave you the basic overview. So now for the UL testing and listings. First off, the UL stands for Underwriters Laboratory. They are a third party which not only creates testing standards and performs the tests, but also certifies products as safe. And mostly these certifications are around fire and disaster safety. So the UL 1642 is a cell level test. The 1973 is a pack or module level test, and the 9540 is a system level test. These are certifications. Again, 1642, 1973, and 9540 are certifications. The 9540A is a test protocol, and this is separate from the above certifications. It is not a certification in itself, it's just a test protocol. So we're going to talk about why you need to care about these and where they might be needed as well. UL certifications are going to be needed for any residential system where your building codes are enforced or where your install might be inspected. Each authority having jurisdiction at each level is going to be different. They're going to interpret codes differently, and even different inspectors are going to interpret codes differently. But regardless of this being a requirement or not, it is always recommended as a UL listed product basically has been certified and tested as safe, whereas a non-UL listed product may or may not be safe. There's really no way to know. You should definitely check with your AHJ to be sure you know what they require. And additionally, even if you're living off grid and you're not going to have any problems with your AHJ, two things to consider is one, at the time of sale, your property will be inspected most likely, and it will need to meet the fire code and building codes at that time. And for insurance purposes, let's say there was a disaster and a fire did burn down your house, I can definitely imagine your insurance company is going to want to know if your batteries were UL listed. So with that said, let's talk a little bit about what is involved in these tests. Again, the 1642 is, or sorry, what is involved within obtaining these certifications. The 1642 is a cell level test and certification. The tests are similar to the 38.3 tests. They basically abuse the battery, doing these sort of things electrically and mechanically, and they're going to basically evaluate the cell's ability to withstand this abuse. The 1973 is going to be a battery module level test. Again, it's going to abuse the battery with over voltage and over current conditions and evaluate the battery's ability to withstand these with and without the BMS intact. And we have passed both the 1642 and 1973 with no issues. As far as the 9540, this is a system level certification. This is going to not only verify that the battery and inverter are safe, but they're also going to verify the interoperability of the two. So our access and boss configurations have finished testing for up to 36 battery modules in total, and we are in the final reporting phase of this certification. So if there's a specific certification that you need, just go ahead and either email me, I'll put my email at the end of this presentation, or email the sales team here at SimpliPhi Power. So UL 9540A, it's new, we've been getting a lot of questions on it. Let's talk about that. So it's not a certification, it's just a test method. It does not currently affect the other certifications that I mentioned. And it's not a certification in itself. So the 9540A testing, basically they're going to add heat externally and force a thermal runaway event. This is not necessarily required everywhere, but we'll talk about that a bit further in the next slide. This is kind of a chart that lays out the different levels of testing the cells and batteries undergo. Again, demonstrating here that the UL 9540A test is separate from the 9540 listing. It does not currently affect the first edition of 9540. What I want to highlight is that the test report is going to be needed in certain regions and for certain size systems. For example, one region that is often requiring a 9540A test report is New York City. They are often requiring this, and again, depending on your authority having jurisdiction, you might need this for larger and medium-sized systems as well. Make sure to check with them. Cool, so we have covered now the safety in producing a battery, the safety in operating a battery, and those certifications. And now I want to talk a bit about the end of life. So why do we care about battery safety at the end of life? Well, we should care because there's been 6 fires in 2016 alone due to this one recycling facility's consumers not properly disposing of their batteries. So this poor recycling facility, through no fault of their own, really has experienced 6 fires just in 2016. So that brings me to the important point that our batteries are not only recyclable, but they're landfill safe as well. being landfill safe basically means they contain no toxic chemicals, and those toxic chemicals are really heavy metals. This is surprisingly not related to cobalt. Awesome, so now we've covered the full life of the battery, safety-wise. And let's talk a little bit about the installation. I want to make sure everyone has a basic understanding of how to safely install, design, and commission a system. So before installation, I know a lot of our installers, when they have an installation coming up, will just send us their single line diagram and ask for any feedback. And I think that's awesome. I love this diagram here because it shows every single connection. This is great because you don't want to get down to the last second of an installation and realize you forgot a lug, or you've got the wrong size terminal stud to use your lugs on. Really helps you in planning. So I would definitely encourage everyone before installing a system to have a thorough wiring diagram created similar to this. Additionally, I want to let you know that you should hire a professional if you have any doubts about your installation. The professional installers here are definitely going to know about wire sizing and fuse and breaker sizing and where those are required. Breakers and fuses are always a great idea to add safety to a system. In addition, they're likely required at several points in the system to protect the components. And always a good idea to upsize wires as well from the minimum requirement. I don't want to go too into detail there. You can email us with questions, but really this is also up to your AHJ. As far as sizing the battery goes, most of our batteries are rated to C/2 charge and discharge rate. So that means that if you have a 3.8 kilowatt hour battery, you can discharge it or charge it at 1.9 kilowatts. That means you could fully charge it and discharge it in 2 hours. If you have any questions about your specific battery, maybe you want to know the charging set points, be sure to check our website for the spec sheets and other guides around your installation. You can follow this link here. We'll send this out to all of you, the PowerPoint which contains this link. As far as how to personally protect yourself during the installation, make sure you come prepared with a torque wrench here. I'd recommend an insulated one if you can. You want to make sure you calibrate that between jobs. Some nitrile-coated gloves, a dry environment, and some safety glasses. Additionally, some tools you're going to want for your install are an amp clamp and voltmeter. If you're installing flooded lead-acid batteries, you're also going to need an acid-resistant apron, gloves, a face shield, and goggles, in addition to a spill kit. So if you're already frustrated with wearing a mask during this coronavirus pandemic, maybe don't install flooded lead-acid batteries because you're going to need a lot of extra PPE. So during the actual installation, I wanted to highlight the order of commissioning, when to turn what stuff on. So firstly, during your install, make sure your battery's breaker, the built-in breaker on top of them, is flipped off. This will ensure that you don't short the two terminals together while you're, tightening the lugs onto the terminals. Also, don't connect two batteries at significantly different SOCs, states of charge. If you have a system that exists and is fully charged, don't just connect your brand new battery to the existing system. We ship out batteries at about 30% state of charge due to safety regulations, and when they reach the customer, they often think that they are fully charged. That is not the case. You might even see a voltage of 52 or 53 when you first receive the battery. It doesn't mean that it's fully charged. Be sure to fully charge the batteries before connecting them all in parallel and before powering loads with a new battery. So, and let me just clarify, you want to charge new batteries before adding them to an existing bank. You don't need to charge brand new batteries before combining them in parallel and connecting to the charger. So let's review the order of commissioning. You're going to turn on the batteries first once everything is connected, and next you're going to turn on the charger. You're going to connect it to its charging source. So that would be, for example, a charge controller connecting to PV or a inverter charger connecting to the grid. Now, third, do not connect your loads and power those until the batteries are fully charged. Last but not least, we're running ahead here on time. I guess I went through those pretty quickly. I was excited. But the SimpliPhi IQ installer program. I know there's a lot of installers here listening to this presentation, so I wanted to mention what benefits this program has and how you can get started. So our IQ program, for example, we provide this map to our customers. This is where they can find you if you're IQ certified. This is called our Where to Buy map. So this is a great advantage if you're IQ certified for customers to be able to locate people near them who can install our batteries. This is not required to install our batteries, but it does have advantages. I want to show you how to apply. You can apply by clicking this link, and it's going to take you to our website. Hopefully you can see this okay. This is the page where you're going to apply. So you can see you'll get some swag when you are approved, when you're certified, excuse me. And we just need some basic info about you or your company. We also need to know if you have a permit and if you've installed SimpliPhi products before. If you have, make sure to include a couple photos so that we can show off your work if that's all right with you. Also, please send us a copy of your permit or your license, whatever that may be in your area. Awesome. So that wraps up my presentation for today. Guessing we're going to have a bunch of questions come in. So I just wanted to leave some extra time for the Q&A today. Again, thank you everybody for joining, and please feel free to email me directly at this email here, or you can email our sales team with any specific questions. It's just sales@simpliphipower.com. I'm going to open up the Q&A now. Derek, are you able to see the questions?
Yeah, I just brought it up.
Awesome. Okay, so we've got Derek here. He is in charge of all the certifications of our batteries, a very lucky man. So he's going to help me answer any questions that I'm not sure about.
Yeah, it looks like the first one is regarding Canada certifications. In general, of course, as Matt went over, there are specific AHJ requirements, but at the higher level, the UL 1973 and UL 9540 standard do seem to be commonly required, just like in the US. And those standards specifically are applicable in Canada as well. So ANSI approved, CSA, UL, and Canada usable. For any other certifications, more granular certifications, of course, it's best to double check what's required. And oftentimes certifications are acceptable kind of even without the specific Canada approvals. A lot of AHJs will accept the standards across as kind of an alternative compliance path. But UL 1973 and 9540, which is being finalized this week, we have both, and both are applicable to Canada officially.
Awesome. Great answer. So Nancy, I see you have a question here about the order of commissioning of the system. How do you suggest that we set the parameters prior to turning on the system? There's a lot of ways you can do this. My best suggestion would be to connect your batteries to the charge controller or inverter and then program the charging settings immediately. Once they're all charged up, then connect them to your loads and program those settings as well. Oftentimes, also, if you have a battery bank you're getting rid of, if you want to just change the settings to the SimpliPhi settings before connecting your new SimpliPhi batteries and just immediately pull off the other batteries right after changing the settings, that's fine as well. So there's a lot of ways you can do this, but I think ideally, like I said, connect the batteries to a charge controller first and then program the settings there. And then once they're charged, turn on the inverter and get those settings done as well. But they do not need to be necessarily programmed prior to even turning the device, like the inverter charge controller, on. You can just program them immediately upon turning it on. I see a question: in an installation where the batteries rarely get to 80% depth of discharge, is this a problem? Maybe the vast majority of the time they may reach only 50% or less depth of discharge. Yeah, great question. It's not a problem for the batteries to only reach 50% depth of discharge. Not a problem at all. I have customers over 10,000 feet in Colorado. Any problems with your batteries? It also gets to 24 below zero here. So I don't know specifically about the 10,000 feet. Why don't you email us the exact elevation if you have it, and I can touch base with my engineering department. As far as the 24 below zero, I think a great option there is the SimpliPhi battery. It will actually self-protect and not allow charging at too high of a rate below freezing. So that's a great option there. There's also some heating pads you could potentially use to keep the batteries above freezing, but you want to be sure you're not charging them below freezing. Yeah, we'd be happy to help you further design that system. Just email me at my email on the screen. Will the slides be available in a link? Yes, the slides are going to be sent out, or at least a recording of the presentation at the least. So you should be able to find the links. Will you be doing a direct comparison of cross technologies with a catastrophic short circuit? Yeah, I think we touched on that quite a bit during the thermal runaway section. If you have any specific remaining questions, just let me know. Can this be installed to operate EV charging stations? I'm sure it could work to charge an EV, so absolutely. Just give us a email or call, and we can help you design that system. How are the cells protected from thermal runaway? The lithium iron phosphate chemistry is really not going to go into thermal runaway very easily. So I don't know that there's a fuse on each cell necessarily, but all the cells have short circuit protection, as I mentioned. Additionally, there's a BMS built into each pack, of course, that has lots of safety features like over voltage and short circuit protection additionally there. How about AC coupling, absorb, and bulk voltage settings? So the settings We have a guide here on our website on the support tab for whatever equipment you have. We likely have an integration guide for it with the settings contained in there. So I'd recommend you check that out. However, the absorb is generally 56 volts for our 48-volt battery and an absorb time of 6 minutes. And that's when the charger is going to switch from bulk to absorb. So you don't need to set both bulk and absorb. It should be just the same voltage point where bulk ends and absorb begins. One note with AC coupling, I would not recommend leaving float on. Float charging will float from the panels during the day, but then it would also float from the grid at night, so that's really just a waste of power. Any other specific questions about AC coupling, let me know and we can address those. Thanks for the presentation. Awesome. Thanks so much for joining. Hope you liked it. Hope you found some value in this. Awesome, everybody. Thank you so much for joining. I think that's all the questions we got today. Derek, any notes to add?
No, just like you said, feel free to reach out with any other questions.
Awesome. All right. Thanks, everybody.